Okay, so we're going to be looking at the different types of radio decay that exist, or at least the ones, there are more that exist, but we're basically going to be focusing on the three most common ones that we'll be looking at in grade 11. So we have alpha decay, we have beta decay, and we have gamma ray decay. So we'll take these one at a time here. So alpha decay, so first of all, when we talk about decay, remember that's another way of saying radiation. So this is like alpha radiation, beta radiation, gamma ray radiation, okay? So inside the brackets here is the symbol for that radiation particle. So for example, alpha decay is this particle right here. So first of all, actually, let's backtrack. Before we even get into this, I want you to notice how the reaction is written. So notice on the left side of the arrow, there is only one item, and on the right-hand side, there is more than one item. Okay, so all nuclear reactions, so all of these three types of decays are the same way. There's one reactant and multiple products, right? You can see that here. So one reactant, multiple products. So the reactant is always a radioisotope. So meaning it's an isotope of a particular element that does this type of decay. Now these are all naturally formed decays. So this is not something you can force an element to do. It's something that it will naturally do on its own. Okay, so for example, uranium, thorium, and this uranium is also doing a different type of decay. So it looks like it's a decomposition reaction, but it's not a chemical reaction. Okay, so it looks like it's written the way that a chemical reaction is, but it's not. So how can we tell? So first of all, this substance started off as uranium, but if you look at the product side, there is no uranium here. So if you recall anything about chemical reactions, a chemical reaction is where you have elements on the reactant side, and then they rearrange themselves to form different compounds or I should say different compounds on the product side. So there's basically atoms that are being rearranged. So this is not a rearrangement of atoms. What this is the nucleus of this element is changing. That's why this is called a nuclear reaction. Nuclear reaction means that it's a reaction that is changing the nucleus. So obviously the type of decay it is will depend on, well, what change is being done to the nucleus. So let's look at alpha decay. So this particle here is actually what is known as the alpha radiation particle. It's a symbol. So there's two ways of doing it. This is one symbol, or you can sometimes see, you can see it here, the alpha symbol, the 4 and a 2. The alpha symbol can sometimes replace the HE. So let's talk about what that is. This is a particle that has a mass of 4, and the number of protons that's coming off of this nucleus is 2. So what does this mean? It means the nucleus of this uranium is losing 2 protons and 2 neutrons. It's almost like a tiny little fragment of the nucleus has broken off of that uranium. So the resulting piece, this is like the little piece that broke off the uranium, and the element that is left behind is whatever is remaining. So notice, look at the number of protons. We originally had 92 protons. 2 of those protons left, and we're ending up with 90 protons. It's no longer uranium because we've changed the number of protons from 92 to 90. Take a look at the mass number. We went from 238 to 234. It went down by a number of 4. So the mass is lighter. It's 4 particles lighter. So the symbol of the element had to change because this is no longer uranium. Remember, what tells us the element we have is the number of protons. We've lost 2 protons. So we can no longer claim that this is uranium. The nucleus has changed. Okay, so we'll come back to look at beta, but let's look at alpha again. We'll recap this. So here is the original nucleus. Notice how they're showing this particle flying off of this nucleus. This is what happens during alpha decay or alpha radiation. A piece or a fragment of the nucleus breaks off that's composed of 2 protons and 2 neutrons. It has a mass of 4 and an atomic number of 2. So that's why the symbol, the reason why the symbol that can be used is this helium symbol is because actually this particle that fragmented off is equivalent to the nucleus of a helium atom. Now, it's not a helium atom because there's no electrons here. It's only 2 protons and 2 neutrons, but that's why this symbol is sometimes used. Or we can use the alpha symbol from the Greek alphabet, alpha. I'm probably drawing that incorrect, but it's up here. Okay, so that's alpha decay. All right, so if we did an example, let's say we had, let's go backwards. Let's say, let me pull up a periodic table. Okay, so let's say we had platinum, excuse me, platinum 78 and 195. Okay, so let's say our products were this. So the resulting particle has 195 as the mass, 78 as being the number of protons. In order to figure out what it started at originally, you have to essentially add it back in. So originally this must have started off with 80 protons because it's 78 plus 2. So when you look this up on the periodic table, right, it's showing that it's mercury. To figure out the mass that it originally was, remember 4 broke off the nucleus, so you would take your 195 and add back in our 4, which is 199. So this can go either way. Maybe I gave you this and I left a blank like this. Like if it was exactly the same, but I left a blank, by looking to see what the change was from here to here, you can figure out that it was alpha decay. So if you're given a portion of the reaction, you should be able to figure out what the blank of that was, like what, either it could be on the left side or the right side, but fill in the blank according to the change that was made from the nucleus. Okay, so that's alpha decay. Let's take a look now at beta. Okay, so let's look at beta decay. So beta decay is different. Of course, like the setup is the same. Remember, we're changing the nucleus. So the symbol for beta radiation is this right here. Okay, so it's a lowercase e, almost like an electron symbol, or it is a beta symbol from the Greek alphabet, which it almost looks like a capital B with a little bit of a longer line on the left there. Okay, so this beta particle has 0 mass and a change to the atomic number of -1. Okay, so what does that mean? What is happening here? Let's look at the nucleus. Okay, so this nucleus is going from 234 to 234. So I want you to notice that the mass is not changing. So it did when we were looking at alpha decay. Sorry about that, I had to pause the video. So the mass number is not changing. Notice it went from 234, it stayed at 234. The reason for that is because the particle that is fragmenting off of the nucleus this time is actually has no mass at all. In fact, actually, what's happening here is an electron is leaving the atom in this particular case. So you're probably wondering, well, electrons are not in the nucleus. Why is that affecting the nucleus? It's because what happens here is this particular electron, as it fragments off, causes a change in the nucleus to happen. Let's take a look at the number of protons. So the mass doesn't change, but the number of protons actually went up by 1. So we went from 90 protons to 91 protons. So what's actually happening here is when this particle or this electron goes off from the atom, one of the neutrons that was inside of this nucleus becomes a proton, or essentially it went from having no charge to having a charge of +1. So let's look a little bit more in detail. So beta radiation or beta decay, what's happening to the nucleus is it's converting a neutron into a proton. So an electron leaves this atom, and here's our beta symbol, and when this electron leaves, the neutron, one neutron becomes a proton. So it's very different from our alpha particle, as you have noticed, right? So actually, you don't have any protons or neutrons leaving at all. What you're doing is you're essentially adding in a proton. So same thing as when we did the fill in the blanks here. When you're doing beta decay, you can do that. You're expected to do the same type of thing. So let's say we had, I'm just looking at my periodic table. Okay, so let's say we had tungsten 74 and a mass of 183. Okay, so if this is beta decay, right? So let's say we don't know what the product is, but this is beta decay. When we're looking at the, oh my goodness, pardon me. So we have 0 on top, -1 down. So the mass number does not change. Remember that we are not changing the mass. However, this electron, when it leaves, will convert a neutron into a proton, which means it should have 1 extra proton there. So what ends up happening, if you look this up, we have a new element, the symbol Re. So same thing, you can be given a reaction like this and you'll have blanks that are there for you to fill in, but you'll always have enough information given that you can figure out what the missing piece is. Okay, now let's go back and look at gamma radiation. So gamma radiation is actually kind of simplistic to think about. So the gamma particle, so the symbol is like a cursive Y, which is the gamma symbol from the Greek alphabet. And actually, it has no mass and no charge. So the gamma ray particle is really a high energy wave. It's almost like it's a burst of energy that is let off when you have this decay happening. So gamma ray decay never happens alone. It either happens with beta or with alpha. So you'll never just have gamma particles that are being let off on their own. It's kind of like a side effect that can happen sometimes when the other types of reactions occur. So notice this reaction that's written is exactly the same as the one up here, but there's an additional product that's made, 2 gamma particles. Actually, don't even worry about the number 2. That just means there are 2 energy waves that are being released. What matters is that this is the gamma particle.